Combinatorics is a field of mathematics devoted to counting that can be helpful to studying probabilities. For example, we can use factorials, which feature prominently in combinatorics, to calculate probabilities instead of painstakingly determining all of the members of the sample space omega and counting subsets within omega for our numerator, the probability of an event. So first, let me explain quickly what factorials are. So if we have 3 factorial, that means we multiply 3 times every integer that's lower than it. So 3 times 2 times 1, and that gives us 6. If we had 4 factorial, then it would be 1 times 2 times 3 times 4, which would give us 24 for 4 factorial. So factorials are key in combinatorics. And so once we know that, then we can start talking about this formula here, which is the number of combinations equation. And as you can see, there's factorials in it a few times. So working with this number of combinations equation that we just had up on the board, the left-hand side of this equation, so the stacked n on top of the k, we read that as n choose k. And this equation is most quickly understood via an example. So if we have 3 coin flips, then n is equal to 3. And if we're interested in the number of ways to get 2 head flips, or as it happens, 2 tail flips, then k is equal to 2. So we would read that as 3 choose 2, and we'd calculate it as follows. So we'd say 3 choose 2, and then we just use our formula here and plug the values in. So we've got n factorial in the top, so that's 3 factorial, and then the denominator consists of k factorial, so 2 factorial for k, times n minus k factorial, which is 3 minus 2 factorial. And simplifying a little bit, the 3 minus 2 becomes 1, and then we can expand out all of these factorials. So in the numerator, we have 3 times 2 times 1, and in the denominator, we have 2 times 1 times 1. So simplifying the numerator, that becomes 6, and 2 times 1 becomes 2. Simplifying a little bit more, 6 over 2 is simply equal to 3. So this 3 choose 2 equation provides us with a 3 that we can use as the numerator for our probability formula. So it's this 3 that's the number of possible outcomes, the number of possible outcomes where we'd have 2 heads from 3 coin flips. And to give you a quick trick for calculating the number of outcomes in omega, our sample space, in the case of coin flipping, this denominator can be calculated with 2 to the power of n, where that n number is again the number of coin flips. So everything in this example so far, we've been working with an n of 3. And so we can have 2 to the power of 3 for our denominator, meaning that our numerator, the number of outcomes of the event, is equal to 3, and our denominator, the number of outcomes in our sample space omega, is 2 to the power of 3, which comes out to 8. And so this comes out to 0.375, and guess what? That's the same number as we had earlier when we were painstakingly creating a sample set of all of the possible events and then counting up the ones where there were 2 heads. So instead of going through that painstaking process, with combinatorics, we can rely on factorials, the number of combinations equation, and tricks like this 2 to the power of n in order to rapidly calculate the probability of a particular event. Nice, feeling confident about the probability theory so far? Up next, I've got some exercises for you.